Today we're going to talk about alpha, beta, and power. A type 1 error is when you reject a true null hypothesis. Alpha is the probability of a type 1 error. This is also when you get a false positive. A type 2 error is when you fail to reject a false null hypothesis. Beta is the probability of a type 2 error, and this is also known as a false negative. When we conduct a hypothesis test, we choose the significance level alpha. We use this value as a criterion for deciding how small a p-value has to be to provide convincing evidence to reject the null hypothesis. You set alpha based on many things. If the consequences of a type 1 error are really expensive or severe, for example, shutting down a water plant, convicting an innocent person, you would need really strong evidence to convince you to reject the null hypothesis. Hence, you would set your alpha to be really small. While you have control over alpha and n, the sample size, you do not have control over beta. In most cases, the null hypothesis is a statement of no effect. No difference, no change, everything's okay, or nothing is suspicious. For our examples today, we will use everything is okay for our null hypothesis. Let's look at examples of type 1 and type 2 errors within context, using the examples that we've done before. For example, if we talk about the trial, our null hypothesis would be innocent. Type 1 error would be convicted an innocent person. Type 2 error would be a guilty person walks. Or a guilty person goes free. With the company cheating you, the null hypothesis would be the company is truthful. A type 1 error would be the truthful company is found cheating. A type 2 error would be a cheating company is found truthful. Or a cheating company was found not cheating you out. When will a type 1 error occur? It happens when the null hypothesis is true, but we draw an unusual sample that leads us to reject the null hypothesis. We set the value of a hypothesis test. This tells us how often we are willing to reject a true null hypothesis. If we rewrite alpha as a conditional probability, alpha equals the probability to reject the null hypothesis when the null hypothesis is true, we can see that alpha is an area under the null hypothesis is true distribution. Let's look at alpha, beta, and power with a left-tailed hypothesis test example. Let our null hypothesis P equal 0.2 and our alternative hypothesis P is less than 0.2, the company is cheating. First, let's set alpha. So we're going to draw a picture of this. And I have my normal distribution curve. And here I would have P. And alpha is the region where we reject the null hypothesis, but the null hypothesis is true. So we're going to set our alpha region first. So this would be our alpha. And remember, alpha is the region where we reject the null hypothesis, but the null hypothesis is true. And remember, this is our sample and distribution. For our null hypothesis, P equals 0.2. When our null hypothesis is true. So P equals 0.2 and HO is true. This region, not highlighted, would be our fail to reject region. Our rejection region, which is our alpha, so don't forget that our alpha is our rejection region, that does not move. Okay, so power is the region where we reject the null hypothesis and the alternative hypothesis is true. So we can move our P and compare this when we increase our power and decrease beta. Okay, so if I were to draw along this here, this rejection region does not move. So it would still be right about here. Okay. And power is the region where we reject the null hypothesis and the alternative is true. Our area on this side is beta. And beta is the area where we fail to reject the null hypothesis, but the null hypothesis is true. And our null hypothesis could change to being true at 0.15. And don't forget, this side here is our fail to reject region, and this side here is our rejection region. So when that region increased, power increased. And this is the sample and distribution. For our alternative hypothesis, p equals 0.15 when our alternative is true. So here, our rejection region, our probability that we made the right decision increased because our power increased. So note, if our null hypothesis is false, there must be some other distribution that is true. This is the alternative hypothesis true distribution, which was the bottom one that we drew. Suppose we know the distribution for our alternative hypothesis is true, and suppose that we know our alternative hypothesis is less than our null hypothesis, which I illustrated in those pictures. We add the alternative hypothesis true distribution to our picture above and shade the region for beta. If we rewrite beta as the probability of fail to reject the null hypothesis when the alternative is true, you can see that beta is an area under the alternative hypothesis true distribution. In order to calculate beta, we must first set alpha. In addition, we need to know the value of the parameter for our alternative hypothesis. For example, we set it to 0.15. Since the parameter value is usually unknowable, we can calculate the value for beta for many different values of the parameter. Note, we won't actually ever calculate beta. So let's talk about the power of the test. So for a criminal trial, the power of the test was correctly finding a guilty person guilty. For a cheating company, it was correctly finding a cheating company cheating. The power of a statistical test is the probability that our hypothesis test, alpha being fixed, will reject the null hypothesis when a particular alternative value of the parameter is true. For example, the alternative hypothesis is true. Power is a function of the value of the true alternative parameter value, just like beta. Power is the probability of correctly rejecting a false null hypothesis, meaning the alternative hypothesis is true. If the null hypothesis really is false, we would like our hypothesis test to show this. The higher the power of the test, the better able our test is at detecting the truth. Power is good. You always want more power. Higher power means smaller beta, less chance of failing to reject the null hypothesis incorrectly. This means you are more confident about a decision to fail to reject the null hypothesis if that's what your hypothesis test leads you to decide, because it is less likely that you've made an incorrect decision to fail to reject the null hypothesis. Less chance of a type 2 error. We will add power to our picture above, which we already did. We talked about that. And power is the probability to reject the null hypothesis when the alternative is true, given the alternative is true. And power is 1 minus beta. Power is the probability of not making a type 2 error. So you can also think of power as the probability of a true positive. The probability of correctly rejecting the null hypothesis. Let's look at the relationship between alpha, beta, and power. So what we're going to do is we're going to change alpha. We're going to increase alpha in this case. What will happen to beta and power? You control this. So if I were to draw my normal curve with my alpha, so we have our probability of 0.2. This is my fail to reject region. Here, I have my original alpha. And if I were to increase my alpha, what would happen to power and what would happen to beta? So if I were to draw the same thing underneath, and I would increase my alpha, so say we increased it out to here, this is my second alpha. So the first one, white, is less than my second one, which I have in blue. And here we know my probability went down to 0.15. This is my fail to reject region. And my rejection region over here. When we increase alpha, so alpha went up, beta went down because this side is beta, which leads power to go up. We reject more often, so fail to reject the null hypothesis less often. So there's a less chance to make a type 2 error here. What if the alternative hypothesis is true? And the alternative hypothesis, given the null hypothesis, is farther apart. What happens to beta and power? We control this. So let's go ahead and draw our original picture. So we have our probability of 0.2. Here we have our alpha, this region here. This is the fail to reject region. This is our rejection region. And they're saying that these are further apart. Meaning our p value gets even smaller because it's further away from it. This is your rejection region. So this right here would be your fail to reject region. And this would be our rejection region. So what happens to all this? Our power goes up and beta goes down. So as they go further apart, power increases and beta decreases. You're more likely to find a cheating company cheated because the company now really is cheating because that beta got even smaller. And then let's look at the relationship if we change the sample size. Increase, in this case, what will happen to beta and power? So n will be going up. So if p equals 0.2, here we have alpha. And as we increase the sample size, our distribution gets closer and closer together. And here, this side would be beta. Again, we'd have something like p equals 0.15. And this is your fail to reject region, your rejection region. And here, as n increases, so n is going up, alpha decreases, and power goes up. So beta and power goes up. Beta goes up, and power goes up. So let's go over the summary, and this you should have read in your textbook. Holding everything else constant, increase in alpha will result in beta decreasing and power increasing. This should make sense because you are more likely to find a null hypothesis false, and your risk of incorrectly failing to reject a false null hypothesis is smaller. Holding everything else constant, if the alternative hypothesis and null hypothesis are farther apart, your test will have more power to detect this. Holding everything else constant, increase in sample size will result in alpha and beta decreasing and power increasing. Remember, alpha and beta are inversely related. Hold an n constant. If I decrease alpha, I will increase beta. If I reduce the chance of sending an innocent person to jail, I increase the chance of letting a guilty person go free. If I reduce the chance of wrongfully accusing a truthful company of cheating, I increase the chance of incorrectly finding a cheating company truthful. Remember, you have only two things under your control, alpha and n.